In lesson 13, we're going to continue to talk about proofs within parallelograms. So let's take a look at this conjecture. And this conjecture says the diagonals, which connects opposite vertices. So if we had a parallelogram here, okay, diagonal would be like this. Okay, there's one diagonal, here's the other diagonal, it connects opposite corners. And then they bisect each other. So remember, that means to split into equal pieces. So on a segment, okay, if a segment is being bisected, it looks like this. Okay, and bisecting each other means both are being split up evenly. So we're going to try and figure this out, or we're going to take a look at the proof. So let's go ahead and look at this. So diagonals of a parallelogram bisect each other, and we're going to look at proving this in two different ways. So let's start by kind of drawing a picture of the diagonals of a parallelogram. So that's what we know. And that what we're trying to prove is that they bisect each other. So this is what we're trying to show or to prove. So let me draw a parallelogram down here. And then let's draw in the diagonals. All right, so there's our parallelogram, and then let's draw in the diagonals, corner to corner. And what we want to do is prove that those diagonals bisect each other, okay? So let's put some letters here to help us. So we've got A, B, C, D, kind of however you wanted to do that. And then let's just call that M. So we are trying to show, okay, trying to prove that BM is congruent to MD. And we're trying to prove that AM is congruent to MC. So those are the two things we're trying to prove in this. And again, we're given that it is a parallelogram. So we know all of the other properties of parallelograms that we have. So kind of thinking about this, it seems to make sense that maybe we're going to be, if we're doing triangle congruence, maybe we want to prove two sets of triangles are congruent so we can steal their pieces. So you can kind of pick whichever set of triangles you want. So this kind of top set here, BCM, is going to be congruent to this bottom one. I think we can prove that, or we can prove left and right. So I'm going to just do left and right. So one of the things we know about parallelograms is that their opposite sides are congruent. So I know those two pieces are congruent. We also know that we've got parallel lines. Okay, and parallel lines would help us with alternate interior angles. So if we thought about AB being parallel to CD, we should be able to get this angle congruent to this angle from alternate interior. Okay, if you kind of think about drawing that Z on there, you see those alternate interior angles. And then we should be able to do either, you could do vertical, or you could do another set of alternate interior. So we also have this set of alternate interior. So if you think about it as this way, you see another set of alternate interior. And then we would see that those two triangles are congruent because now we see two sets of angles in the side in between. So I think we're going to be able to prove the triangles are congruent with angle, side, angle. And we're going to get these kind of angles here by alternate interior. And the side from a property of a parallelogram that opposite sides are equal. Okay, so I'm just kind of writing down some of my plan so that then I can go ahead and get it all kind of typed out. So then when you start to talk about it, you would start to kind of talk with what you're given so you know that it's a parallelogram. And so the first thing I did was maybe talked about that AB and CD are congruent. So AB is congruent to CD because opposite sides in a parallelogram are congruent. Okay, so stating what I know and how I know it. Okay, so how did I know that these are congruent? And that's from opposite sides. Okay, then the next thing we did was used alternate interior angles. So because AB is parallel to CD, I know angle ABD, so this top one, ABD, is congruent to BDC. BDC, okay, and then these other ones, so BAC and BAC is congruent to DCA because they are alternate interior angles. Okay. So that got my set of sides. Okay, so I've got my set of sides here proven. And then I also did this set of angles. Okay, so then I had that set of alternate interior angles, and I have this set of alternate interior angles in my proof. Okay, so we had this is kind of up there in red, the set of sides. And then the first set of angles in blue there. And then this set of angles I have in green in the proof. Okay, so that kind of shows you that we got all of that information into our proof, which was our angle side angle. And that helps us to prove that the triangles are congruent. Okay, so we said all of that so that we could say that the triangles are congruent. Okay, so triangle ABM is congruent to CDM by angle side angle theorem. So you can write ASA if you want to, or angle side angle triangle congruence. And then since the triangles are congruent, we know that BM is congruent to MD. And you can see that here. Okay, so we've got these two. So BM and DM, okay, are congruent. And AM and MC, okay, so A is the first and M is the third. So first and third, and then C and M. So AM to CM, because they are corresponding parts of the congruent triangles. And ultimately, this was what I wanted to prove. So we wanted to prove that BM is congruent to MD, okay, and AM, is congruent to MC, because those were the diagonals being bisected. So we just got in there ultimately was that this equals this and this equals this. So that is going about that through triangle congruence. Okay, another way that you could tackle this would be through rigid motions. So let me delete some of this stuff out of here so we can start fresh. So for rigid motions, that's going to be talking about rotations, translations, that kind of thing. So maybe when you looked at this, okay, you thought, man, that looks like I could rotate one of these triangles around. Okay, so and if I could prove that this triangle rotates 180 degrees around point M, that would force M to be the midpoint. Okay, which would get me to have those two pieces being congruent, BM and MD. Okay, and so in order to do that, a couple different ways you could do that. Maybe you want to prove these triangles are congruent so you know that they would be able to have a rigid motion on. So in order to talk about that, you would know that BC is congruent to AD because opposite sides of a parallelogram. CD is congruent to AB because opposite sides of a parallelogram. And then BD congruent to itself. So that would prove that those two triangles are congruent by side, side, side. So therefore, you would be able to rotate around and all of the parts would land on top of each other, so M would have to be in the middle. Okay, so when you're going to say this in your proof, you would be saying BC is congruent to AD and CD is congruent to AB because opposite sides of a parallelogram are congruent. Okay, that's how you knew those. Then you would go ahead and do the reflexive, or that same segment. Also, BD is congruent to BD because it is the same segment. Therefore, since triangle BCD is congruent to triangle, okay, so we did BCD is congruent to DAB by side, side, side. Okay, so how do you know? So by side, side, side. We know there is a rigid motion. Okay, so we know we can rotate triangle BCD 180 degrees around point M, and C will land on A because BC and CD are the same length as AD and AB. Therefore, M must be the midpoint, meaning BM is congruent to MD. Okay, so proving those two triangles are congruent, so then you know that you'll be able to rotate this around so that D will land on B, B will land on D, and then C would land on A. Then you essentially, okay, so you essentially then would need to do that again, state this similar argument, okay, very similar argument, in order to prove that happens again for this triangle onto the next one. And I don't think that we need to say A, B, and C, D again because you already did that. Okay, so you already have AB congruent to CD and BC congruent to AD. So you could say we also know triangle, or we also know AC is congruent to AC because it is the same segment. So triangle ABC, this blue one, is congruent to triangle CDA by side, side, side. And then you would say something again about rotating. Okay, so then rotating. Therefore, we can rotate triangle ABC around point M. Until A coincides with C, and B would land or coincide with D because AB and BC are the same length as CD and AD. Therefore, M is the midpoint of AC as well. So AM and MC are congruent. Okay, so something like that. where you prove that you can rotate it around and that all the points will land on top of each other. So then you ended up getting those two diagonals to be congruent as well. Okay, so you got this, and then you got, or not congruent, but you got the diagonals to bisect each other. So you ultimately talked about how M was the midpoint of both. So getting BM congruent to MD. And you also proved that this one was congruent to this one, AM to MC. So you did prove that they bisected each other. Okay, so when you're doing rigid motions, you just got to make sure that you are proving that the points will actually land on the other points. One way to do that is by proving that the triangles are congruent so that when they rotate around, they will land. Okay, another option that you might look into is by, you know, your parallel lines again. You could talk about the angles being the same, the alternate interior angles. So then when it rotates around, B would land on D because of BC being the same length and at the same angle. So then that would have just changed a little bit of your language in here. So then we have something called the converse of a statement. So converse is when you flip the initial claim, okay, called the hypothesis, and the final portion called the conclusion. So you switch these after the if and the then. So we would, instead of saying if a quadrilateral is a parallelogram, then diagonals bisect each other, we would say if it's, meaning quadrilateral. So if a quadrilateral has diagonals that bisect each other, then it is a parallelogram. Okay, so you interchange. So this one was saying its diagonals bisect each other. So if a quadrilateral has diagonals that bisect each other, then the quadrilateral is a parallelogram. So then it's a parallelogram. So if that happens to be true, if both of these are true, so if a parallelogram forces diagonals to bisect each other and bisecting diagonals force a parallelogram, okay, if both statements are true, then we can say it with an if and only if statement. So then what we would do is take these two statements, so what's underlined here, we would say a quadrilateral is a parallelogram if and only if its diagonals bisect each other. Okay, so you see the two statements put together with if and only if in the middle. So a quadrilateral is a parallelogram, and then you see if and only if its diagonals bisect each other. So now that did not happen the other day. Remember when we said all rectangles are parallelograms? And then we also, which was true, and then the converse of that, or the flip of that, is that all parallelograms are rectangles, which was false. Okay, so then this one we would not put together as what's called a biconditional with if and only if. So we would not do that since this was true, but this was false. So the converse was false. The flip of it was false. So in the lesson summary, it again talks about that if and only if language, and that's only happening if both statements are true, if a statement's converse is true as well. So both statements means forward. I like to think of it as reading it forwards and backwards. Okay, so reading it forwards is true, and backwards is true. So if you're reading this statement here, it says if a quadrilateral has diagonals that bisect each other, then it's a parallelogram. Okay, so you would see, you know, this diagonals bisect each other as the first part, then it's a parallelogram as the second. So the flip of that is if a quadrilateral is a parallelogram, then the diagonals bisect each other. So and you're just looking into it's just going to go through proving each way. So starting with bisecting diagonals, getting to parallelogram, and then it's going to go through starting as a parallelogram and getting bisecting diagonals. Okay, so here's that part 2.